A gas compressor is a mechanical device that increases the pressure of a gas by reducing its volume. An air compressor is a specific type of gas compressor. Compressors are similar to pumps, both increase the pressure on a fluid and both can transport the fluid through a pipe. As gases are compressible, the compressor also reduces the volume of a gas. Liquids are relatively incompressible. While some can be compressed, the main action of a pump is to pressurize and transport liquids. Types of compressors. The main types of gas compressors are illustrated and discussed below. Centrifugal compressors. Centrifugal compressors use a rotating disc or impeller in a shaped housing to force the gas to the rim of the impeller, increasing the velocity of the gas. A diffuser section converts the velocity energy to pressure energy. They are primarily used for continuous, stationary service in industries such as oil refineries, chemical and petrochemical plants and natural gas processing plants. Their application can be from 100 horsepower to thousands of horsepower. With multiple staging, they can achieve high output pressures greater than 10,000 psi. Many large snowmaking operations use this type of compressor. They are also used in internal combustion engines as superchargers and turbochargers. Centrifugal compressors are used in small gas turbine engines or as the final compression stage of medium-sized gas turbines. Diagonal or mixed flow compressors. Diagonal or mixed flow compressors are similar to centrifugal compressors, but have a radial and axial velocity component at the exit from the rotor. The diffuser is often used to turn diagonal flow to an axial rather than radial direction. Axial flow compressors. Axial flow compressors are dynamic rotating compressors that use arrays of fan-like airfoils to progressively compress the working fluid. They are used where there is a requirement for a high flow rate or a compact design. The arrays of airfoils are set in rows, usually as pairs, one rotating and one stationary. The rotating airfoils, also known as blades or rotors, accelerate the fluid. The stationary airfoils, also known as stators or vanes, decelerate and redirect the flow direction of the fluid, preparing it for the rotor blades of the next stage. Axial compressors are almost always multi-staged, with the cross-sectional area of the gas passage diminishing along the compressor to maintain an optimum axial Mach number. Beyond about 5 stages or a 4:1 design pressure ratio, variable geometry is normally used to improve operation. Axial compressors can have high efficiencies. Around 90% polytropic at their design conditions. However, they are relatively expensive, requiring a large number of components, tight tolerances and high-quality materials. Axial flow compressors can be found in medium to large gas turbine engines, in natural gas pumping stations, and within certain chemical plants. Reciprocating compressors. Reciprocating compressors use pistons driven by a crankshaft. They can be either stationary or portable, can be single or multi-staged, and can be driven by electric motors or internal combustion engines. Small reciprocating compressors from 5 to 30 horsepower are commonly seen in automotive applications and are typically for intermittent duty. Larger reciprocating compressors well over 1000 HP are commonly found in large industrial and petroleum applications. Discharge pressures can range from low pressure to very high pressure. In certain applications, such as air compression, multi-stage double-acting compressors are said to be the most efficient compressors available, and are typically larger, and more costly than comparable rotary units. Another type of reciprocating compressor is the swashplate compressor, which uses pistons moved by a swashplate mounted on a shaft. Household, home workshop, and smaller job site compressors are typically reciprocating compressors 1 or 1/2 HP or less with an attached receiver tank. Ionic liquid piston compressor. An ionic liquid piston compressor, ionic compressor or ionic liquid piston pump is a hydrogen compressor based on an ionic liquid piston instead of a metal piston as in a piston metal diaphragm compressor. Rotary screw compressors. Rotary screw compressors use two meshed rotating positive displacement helical screws to force the gas into a smaller space. These are usually used for continuous operation in commercial and industrial applications and may be either stationary or portable. Their application can be from 3 horsepower to over 1,200 horsepower and from low pressure to moderately high pressure. Rotary screw compressors are commercially produced in oil-flooded, water-flooded and dry type. The efficiency of rotary compressors depends on the air dryer, and the selection of air dryer is always 1.5 times volumetric delivery of the compressor. Rotary vane compressors. Rotary vane compressors consist of a rotor with a number of blades inserted in radial slots in the rotor. The rotor is mounted offset in a larger housing that is either circular or a more complex shape. As the rotor turns, blades slide in and out of the slots, keeping contact with the outer wall of the housing. Thus, a series of decreasing volumes is created by the rotating blades. Rotary vane compressors are, with piston compressors, one of the oldest of compressor technologies. With suitable port connections, the devices may be either a compressor or a vacuum pump. They can be either stationary or portable, can be single or multi-staged, and can be driven by electric motors or internal combustion engines. Dry vane machines are used at relatively low pressures for bulk material movement, while oil-injected machines have the necessary volumetric efficiency to achieve pressures up to about 13 bar in a single stage. A rotary vane compressor is well suited to electric motor drive and is significantly quieter in operation than the equivalent piston compressor. Rotary vane compressors can have mechanical efficiencies of about 90%. Scroll compressors. A scroll compressor, also known as scroll pump and scroll vacuum pump, uses 2 interleaved spiral-like vanes to pump or compress fluids such as liquids and gases. The vane geometry may be involute, Archimedean spiral, or hybrid curves. They operate more smoothly, quietly, and reliably than other types of compressors in the lower volume range. Often, one of the scrolls is fixed, while the other orbits eccentrically without rotating, thereby trapping and pumping or compressing pockets of fluid between the scrolls. Due to minimum clearance volume between the fixed scroll and the orbiting scroll, these compressors have a very high volumetric efficiency. This type of compressor was used as the supercharger on Volkswagen G60 and G40 engines in the early 1990s. Diaphragm compressors. A diaphragm compressor is a variant of the conventional reciprocating compressor. The compression of gas occurs by the movement of a flexible membrane, instead of an intake element. The back-and-forth movement of the membrane is driven by a rod and a crankshaft mechanism. Only the membrane and the compressor box come in contact with the gas being compressed. The degree of flexing and the material constituting the diaphragm affects the maintenance life of the equipment. Generally, stiff metal diaphragms may only displace a few cubic centimeters of volume because the metal cannot endure large degrees of flexing without cracking, but the stiffness of a metal diaphragm allows it to pump at high pressures. Rubber or silicone diaphragms are capable of enduring deep pumping strokes of very high flexion, but their low strength limits their use to low pressure applications, and they need to be replaced as plastic embrittlement occurs. Diaphragm compressors are used for hydrogen and compressed natural gas as well as in a number of other applications. The photograph included in this section depicts a 3-stage diaphragm compressor used to compress hydrogen gas to 6,000 psi for use in a prototype compressed hydrogen and compressed natural gas fueling station built in downtown Phoenix, Arizona by the Arizona Public Service Company. Reciprocating compressors were used to compress the natural gas. The prototype alternative fueling station was built in compliance with all of the prevailing safety, environmental and building codes in Phoenix to demonstrate that such fueling stations could be built in urban areas. Air bubble compressor, also known as a trompe. A mixture of air and water generated through turbulence is allowed to fall into a subterranean chamber where the air separates from the water. The weight of falling water compresses the air in the top of the chamber. A submerged outlet from the chamber allows water to flow to the surface at a lower height than the intake. An outlet in the roof of the chamber supplies the compressed air to the surface. A facility on this principle was built on the Montreal River at Ragged Chutes near Cobalt, Ontario in 1910 and supplied 5,000 horsepower to nearby mines. Hermetically sealed, open, or semi-hermetic. Compressors used in refrigeration systems are often described as being either hermetic, open or semi-hermetic, to describe how the compressor and motor drive are situated in relation to the gas or vapor being compressed. The industry name for a hermetic is hermetically sealed compressor, while a semi-hermetic is commonly called a semi-hermetic compressor. In hermetic and most semi-hermetic compressors, the compressor and motor driving the compressor are integrated, and operate within the pressurized gas envelope of the system. The motor is designed to operate in, and be cooled by, the refrigerant gas being compressed. The difference between the hermetic and semi-hermetic is that the hermetic uses a one-piece welded steel casing that cannot be opened for repair. If the hermetic fails, it is simply replaced with an entire new unit. A semi-hermetic uses a large cast metal shell with gasketed covers that can be opened to replace motor and pump components. The primary advantage of a hermetic and semi-hermetic is that there is no route for the gas to leak out of the system. Open compressors rely on either natural leather or synthetic rubber seals to retain the internal pressure, and these seals require a lubricant such as oil to retain their sealing properties. An open pressurized system such as an automobile air conditioner can leak its operating gases, if it is not operated frequently enough. Open systems rely on lubricant in the system to splash and pump components and seals. If it is not operated frequently enough, the lubricant on the seals slowly evaporates, and then the seals begin to leak until the system is no longer functional and must be recharged. By comparison, a hermetic system can sit unused for years, and can usually be started up again at any time without requiring maintenance or experiencing any loss of system pressure. The disadvantage of hermetic compressors is that the motor drive cannot be repaired or maintained, and the entire compressor must be removed if a motor fails. A further disadvantage is that burnt-out windings can contaminate whole systems, thereby requiring the system to be entirely pumped down and the gas replaced. Typically, hermetic compressors are used in low-cost factory-assembled consumer goods where the cost of repair is high compared to the value of the device, and it would be more economical to just purchase a new device. An advantage of open compressors is that they can be driven by non-electric power sources, such as an internal combustion engine or turbine. However, open compressors that drive refrigeration systems are generally not totally maintenance-free throughout the life of the system, since some gas leakage will occur over time. Thermodynamics of gas compression. Isentropic compressor. A compressor can be idealized as internally reversible and adiabatic, thus an isentropic steady-state device, meaning the change in entropy is zero. By defining the compression cycle as isentropic, an ideal efficiency for the process can be attained, and the ideal compressor performance can be compared to the actual performance of the machine. Isentropic efficiency of compressors is the enthalpy at the initial state, is the enthalpy at the final state for the actual process, is the enthalpy at the final state for the isentropic process, minimizing work required by a compressor, comparing reversible to irreversible compressors, comparison of the differential form of the energy balance for each device, axial compressor, reversible compressor. The right-hand side of each compressor type is equivalent, thus rearranging. By substituting the no equation into the last equation and dividing both terms by T. Furthermore, and T is absolute temperature which produces, or, therefore, work-consuming devices such as pumps and compressors require less work when they operate reversibly. Effect of cooling during the compression process. Isentropic process involves no cooling. Polytropic process involves some cooling. Isothermal process involves maximum cooling. By making the following assumptions, the required work for the compressor to compress a gas from to is the following for each process, assumptions, and are the same for each process. All processes are internally reversible, the gas behaves like an ideal gas with constant specific heats. Isentropic, polytropic, isothermal. By comparing the three internally reversible processes compressing an ideal gas from to, the results show that isentropic compression requires the most work in and the isothermal compression, or, requires the least amount of work in. For the polytropic process, work in decreases as the exponent, n, decreases, by increasing the heat rejection during the compression process. One common way of cooling the gas during compression is to use cooling jackets around the casing of the compressor. Compressors in ideal thermodynamic cycles, ideal Rankine cycle 1-2 isentropic compression in a pump, ideal Carnot cycle 4-1 isentropic compression, ideal Otto cycle 1-2 isentropic compression, ideal Diesel cycle 1-2 isentropic compression, ideal Brayton cycle 1-2 isentropic compression in a compressor, ideal vapor compression refrigeration cycle 1-2 isentropic compression in a compressor. Note: the isentropic assumptions are only applicable with ideal cycles. Real-world cycles have inherent losses due to inefficient compressors and turbines. The real-world system are not truly isentropic but are rather idealized as isentropic for calculation purposes. Temperature. Compression of a gas increases its temperature, often referred to as the heat of compression. Where, or, and, so, in which P is pressure, V is volume, N takes different values for different compression processes, and 1 and 2 refer to initial and final states. Adiabatic. This model assumes that no energy is transferred to or from the gas during the compression, and all supplied work is added to the internal energy of the gas, resulting in increases of temperature and pressure. Theoretical temperature rises. With T1 and T2 in degrees Rankine or kelvins, P2 and P1 being absolute pressures and K equals ratio of specific heats. The rise in air and temperature ratio means compression does not follow a simple pressure to volume ratio. This is less efficient, but quick. Adiabatic compression or expansion more closely model real life when a compressor has good insulation, a large gas volume, or a short time scale. In practice there will always be a certain amount of heat flow out of the compressed gas. Thus, making a perfect adiabatic compressor would require perfect heat insulation of all parts of the machine. For example, even a bicycle tire pump's metal tube becomes hot as you compress the air to fill a tire. The relation between temperature and compression ratio described above means that the value of N for an adiabatic process is K. Isothermal. This model assumes that the compressed gas remains at a constant temperature throughout the compression or expansion process. In this cycle, internal energy is removed from the system as heat at the same rate that it is added by the mechanical work of compression. Isothermal compression or expansion more closely models real life when the compressor has a large heat exchanging surface, a small gas volume, or a long time scale. Compressors that utilize inter-stage cooling between compression stages come closest to achieving perfect isothermal compression. However, with practical devices perfect isothermal compression is not attainable. For example, unless you have an infinite number of compression stages with corresponding intercoolers, you will never achieve perfect isothermal compression. For an isothermal process, N is 1, so the value of a work integral for an isothermal process is. When evaluated, the isothermal work is found to be lower than the adiabatic work. Polytropic. This model takes into account both a rise in temperature in the gas as well as some loss of energy to the compressor's components. This assumes that heat may enter or leave the system, and that input shaft work can appear as both increased pressure and increased temperature above adiabatic. Compression efficiency is then the ratio of temperature rise at theoretical 100% versus axial. Polytropic compression will use a value of N between 0 and infinity. For the typical case where an effort is made to cool a gas compressed by an approximately adiabatic process, the value of N will be between 1 and K. Staged compression. In the case of centrifugal compressors, commercial designs currently do not exceed a compression ratio of more than a 3.5 to 1 in any one stage. Since compression generates heat, the compressed gas is to be cooled between stages, making the compression less adiabatic and more isothermal. The interstage coolers typically result in some partial condensation that is removed in vapor-liquid separators. In the case of small reciprocating compressors, the compressor flywheel may drive a cooling fan that directs ambient air across the intercooler of a 2 or more stage compressor. Because rotary screw compressors can make use of cooling lubricant to remove the heat of compression, they very often exceed a 9-to-1 compression ratio. For instance, in a typical diving compressor the air is compressed in 3 stages. If each stage has a compression ratio of 7-to-1, The compressor can output 343 times atmospheric pressure. Prime movers. There are many options for the prime mover, or motor that powers the compressor. Gas turbines power the axial and centrifugal flow compressors that are part of jet engines. Steam turbines or water turbines are possible for large compressors. Electric motors are cheap and quiet for static compressors. Small motors suitable for domestic electrical supplies use single-phase alternating current. Larger motors can only be used where an industrial electrical three-phase alternating current supply is available. Diesel engines or petrol engines are suitable for portable compressors and support compressors. In automobiles and other types of vehicles, diesel or gasoline engines' power output can be increased by compressing the intake air, so that more fuel can be burned per cycle. These engines can power compressors using their own crankshaft power, or use their exhaust gas to drive a turbine connected to the compressor. Applications. Gas compressors are used in various applications where either higher pressures or lower volumes of gas are needed. In pipeline transport of purified natural gas from the production site to the consumer, a compressor is driven by a gas turbine fueled by gas bled from the pipeline. Thus, no external power source is necessary. Petroleum refineries, natural gas processing plants, petrochemical and chemical plants, and similar large industrial plants require compressing for intermediate and end product gases. Refrigeration and air conditioner equipment use compressors to move heat in refrigerant cycles. Gas turbine systems compress the intake combustion air. Small volume purified or manufactured gases require compression to fill high-pressure cylinders for medical, welding, and other uses. Various industrial, manufacturing, and building processes require compressed air to power pneumatic tools. In the manufacturing and blow molding of PET plastic bottles and containers. Some aircraft require compressors to maintain cabin pressurization at altitude. Some types of jet engines such as turbojets and turbofans, compress the air required for fuel combustion. The jet engine's turbines power the combustion air compressor. In scuba diving, hyperbaric oxygen therapy, and other life support devices, compressors put breathing gas into small volume containers, such as diving cylinders. In surface-supplied diving, an air compressor frequently supplies low-pressure air for breathing. Submarines use compressors to store air for later use in displacing water from buoyancy chambers to adjust depth. Turbochargers and superchargers are compressors that increase internal combustion engine performance by increasing the mass flow of air inside the cylinder, so the engine can burn more fuel and hence produce more power. Rail and heavy road transport vehicles use compressed air to operate rail vehicle or road vehicle brakes and various other systems. Service stations and auto repair shops use compressed air to fill pneumatic tires and power pneumatic tools. Fire pistons and heat pumps exist to heat air or other gases, and compressing the gas is only a means to that end. In the United States, there were 300 gas compressor manufacturers in 2011 producing compressors for all of these uses. Although these factories were classified as small business, the total 2011 sales for gas and air compressors was over $9 billion. See also. References